Good morning to all of you. I welcomes to all in our lecture series on solid state physics. In our last class we have been discussed about the Van Laue treatment or the so called Laue's equations, or this equations is describes the conditions of the diffraction or the conditions for the constructive interference of the scattered X-rays when the scattered X-rays is going to be considered that the rays has been scattered from the any two arbitrary atoms in the lattice structure. So these things we have been discussed, and we can say that application of this Laue's equation today we are going to discuss, that is nothing but to find out the atomic scattering factor. So today we are going to be discuss in detail about atomic scattering factor. So to derive the Laue's equation, we have been considered the two arbitrary atoms which are separated by a distance r, and the incident beam incidents on A and B atom and scatters along n2 cap direction, and on the base of conditions whatever we have been derived in our last video, that will be the so called Laue's equations. So here we have been considered the two atoms on which the incident X-ray is going to be scattered, but we have also discussed in our last class, that means whenever we have been discussed about the X-ray diffraction, I will give the link of this discussion or this video, X-ray diffraction video, in the description of this today's video. So whenever we have been discussed the basics of X-ray diffraction, at that time we have been perceived that when the X-ray interacts with the atom, that means X-ray interacts with individual electrons present in the atom, the electron will be vibrate with the frequency of the X-ray, and then this electron will be radiate the same frequency in which it will be vibrates. So in detail I have been discussed in that video. I will give that link that you have to follow. And also in that video we have been discussed another thing is that suppose this is one atom, this is another atom, and suppose this is 1 and 2 are the scattered rays from 2 electrons of this atom, 3 and 4 are the 2 scattered beams from the 2 electrons of the atom B. So there we have been discussed that the path difference or phase difference between 1 and 2 rays is very negligible. Likewise 3 and 4, the path difference or the phase difference is very negligible, because the 2 electrons are present in the atom and the distance between the 2 electrons is very small, so that we can consider the path difference is negligible, not zero, negligible. That means we can consider the 1 and 2 beams, when they are going to be interfere with each other, we can get the constructive interference because the path difference is 0. But significant path difference we can found if we have to consider ray 1 with 3, ray 1 with 4, like that. But that negligible path difference will be creates overall path difference, due to which if I am going to be add the intensity of scattered beam of 1 and 2, and if I am going to take the intensity of the scattered beam of the atom A, will be not be same. That means what I am going to say, that if we have to consider the intensity of the scattered beam 1 is suppose 2, the value is 2, and the intensity of another electron, scattered electron, that is 2, the second beam, suppose that is also 2, so we can get the net intensity of this scattered beam of the atom will be 4, because this ray have the intensity suppose 2, okay, and this ray have the intensity also 2, because these are the 2 electrons. So the net intensity scattered of the scattered beam from this atom should have to be 4, but experimentally it is not so. Experimentally it is less than the 4, less than the 4. So on the base of this concept we have to define and derive the atomic scattering factor. First, whatever I have been explained, those things I have been written on the note in our today's discussion here. What I have been written here in our previous section means I am telling about the Van Laue treatment or Van Laue equations. We have discussed that diffraction conditions given by Laue are concerned with the scattering of X-rays from point scattering centers arranged in the space lattice. So here the point scattering centers are nothing but the atoms. Here I am, you have to write in bracket atoms, okay. And also we have been studied the way in which the individual electron scatters. These things we have been also studied in our previous lectures. So here one can imagine that the amplitude of radiation scattered by an atom, the amplitude of radiation scattered by an atom will be equal to the product of the amplitude of the radiation of the scattered by a single electron and the number of electrons or atomic number present in the atom, what I discussed. That means, suppose here once again I am going to be explain for you. Suppose this is our atom, okay. X-ray incidents over this atom, X-ray incidents over this atom. So this atom, suppose it has 5 electrons. Suppose it has 5 electrons: hydrogen, helium, lithium, beryllium, boron. Suppose this is the boron atom having the 5 electrons. So when X-ray will be incident on this atom, these all the electrons will be vibrate with X-ray frequency, and they are going to be radiate the radiations, which will be nothing but called as the so-called diffraction. So as these all are the electrons, and we are going to be expect their characteristics will be same, then all individual scattered radiations have the same amplitude. So same thing it has been written in the language I am going to explain. Suppose this electron radiates the scattered radiation and have the amplitude, suppose I told that it is 2, suppose the amplitude is 2, suppose. So if each electron have amplitude will be the 2, then the net scattered radiation of the atom, or the amplitude of net scattered of the X-ray of this atom will be how much? It will be 2 into the number of electron is present in this atom will be 5. 2 into 5, this is the amplitude of scattered radiation of each electron and into number of electrons. this number of electrons is nothing but our atomic number. Okay, so if we have to consider one atom and its amplitude of scattered radiation, whole atom, amplitude of scattered radiation of whole atom, theoretically it will be equal to how much? The scattered radiation amplitude of each electron into total number of electrons, or that is nothing but our Z, or atomic number. Atomic number means equal to number of electrons present in the atom. So here it is 5 in case of boron. But experimentally, so what will the total value? Total value should have to be 10, right? Total value should have to be 10. But it is not so experimentally. Experimentally, it is not equal to Z. It is less than that of the 10, whatever we can found experimentally. So we could not found this much value experimentally. So this same thing whatever I discussed, it is written. So here one can imagine that the amplitude of radiation scattered by an atom will be equal to the product of the amplitude. Suppose the amplitude we have to take, suppose this is 2, and the radiation scattered by a single electron, amplitude of radiation scattered by the single electron, and this is, it is written product of, okay, product of amplitude, that is 2, into number of electrons present in the atom, that is 5. But practically it is not possible, because scattered radiations from each electron of an atom not exactly are in same phase, or not exactly we can say path difference equal to 0. So if these scattered radiations will be are in phase, then we can get the constructive interference over here. But as we discussed in our last video, whenever I discussed about the X-ray, introduction to the X-ray diffraction, I told to you that this ray have very negligible path difference, or negligible phase difference, very negligible phase difference. So due to that negligible phase difference, this experimental value will be not matched with the theoretical value. So, but practically it is not possible, because scattered radiation from each electron of an atom not exactly are in same phase, or the so-called path difference not equal to 0. Path difference between, suppose I am going to take this ray and this ray, the path difference is approximately tends to 0. So we can say these scattered radiations have negligible path difference, due to which the amplitude of radiation scattered by a single atom is not necessarily equal to the product of the amplitude of the radiation scattered by a single electron and the number of electrons present in the atom. The same sentence I have written for your clear understanding. Present in the atom, you have to write. I missed it. So due to this negligible path difference between these rays, we could not found the experimental and theoretical value will be exactly same. So same thing it has been written. It is not necessarily equal to the product of the amplitude of radiation scattered by a single electron and the number of electrons present in the atom. Okay, so it is generally less than this value. In general, the value will be less than that predicted value of theory. So theoretically what we can predict over here, it will be 10, but actually it is less than 10, because these rays are not exactly same phase. It is minutely or very negligible path difference we can found between these rays. Okay. So now we can define a term, that is atomic scattering factor or form factor, that is represented by small f by a ratio between the amplitude of radiation scattered from an atom. It is in quoted. I have been written this sentence with in quoted. So to amplitude of radiation scattered from an atom to the amplitude of scattered from an isolated electron. Amplitudes of radiation. Here a small mistake was there. So this form factor or the scattering factor, atomic scattering factor, or it will be also called as form factor F, by a ratio between amplitude of radiation scattered from an atom to the amplitude of radiation scattered from an isolated electron. That is F equal to amplitude of radiation scattered from an atom divided by amplitude of radiation scattered from an electron. That is in mathematically or with this example, if we are going to take, then it will be the numerator part. Theoretically I am going to be tell to you that the numerator part will be the 2 into 5 divided by amplitude of radiation scattered by an electron divided by 5. So it has to be 5. So theoretically we can get the answer will be 5, will be nothing but atomic number, should have to be atomic number. But in general this F is less than that of the Z or atomic number of that atom. Okay. So to calculate F, consider an atom containing electrons arranged in a spherical symmetric configuration around its center, which is taken as origin, and an electron is placed at the center as shown in figure 1. The figure 1 will be like this. Okay. So you have to draw the figure, this figure over here. Okay. This is the figure number 1. This is the figure number 1. You have to draw this figure after writing this much here. To explain, I have been drawn separately this figure, because if I want to explain the next place, I have to again come back to the previous page, so that I have been drawn. But you have to do this figure here. Okay. So in this figure 1, this represents one atom, okay, in which the electrons are distributed over spherically and symmetrically. F, to calculate F, consider an atom containing electrons arranged in a spherically symmetric configuration around its center. The electrons are distributed in the atom with spherically symmetrically manner, and at the center of the atom also we have to consider a electron has to be present here. So at the center one electron, here I have been written E, one electron will be present here, and other electrons, the atoms and it's all other electrons. Suppose we are going to consider boron having the 5 electrons. These 5 electrons are distributed inside the atom, and an extra electron we have to imagine that will be present at the center. This is the things whatever written here. Now let R be the radius of the atom, r is the radius of the atom. This is the radius of the atom. Rho r is the charge density at a distance at a point r. This is the charge density, represents the charge density, means charge per unit volume. Okay, consider a small volume dv at r. Hence the charge located at r is suppose we have to consider a small volume. This is a small volume. Okay, so this is a small volume we have to consider, which is situated at a distance r from the center. Hence the charge inside this volume will be how much? Charge density into this volume, that is rho r into dv. Here n1 cap and n2 cap represent the directions of the incident and scattered beam respectively. So in this figure, n1 and n2, these two rays are the incident beam and these two rays are the scattered beams. So these two rays are incident, these two rays are scattered beams. Now consider the phase difference between the wave scattered from the charge, this one, rho r dr. Here r is the function, not multiplied with rho. Okay, this rho r means here r is the function, that means charge density at point r. At point, suppose r, means at r distance the charge density is rho. Here r is the function to the rho, not multiplied with r, not multiplied with rho. Okay, so now consider the phase difference between the wave scattered from the charge, this one, and that scattered from the electron which is at the center of atom O. Now we have to consider the phase difference between the two rays, between these two rays. One ray which is scattered from this charge, and another scattered ray which is scattered from the origin where an electron is present. So now what will be the path difference between these two rays? This situation is very much similar with Lauge treatment, whatever we have been discussed in that video, in the Lauge conditions video. You can see that here we have been considered the two atoms, right? Here we have been considered one electron, one charge. Okay, so here also the two interacted particles or interacted matters, same thing. See, the same situation if I am going to be consider, if I am going to be match over this one, then it will be, instead of A I have been considered a charge, instead of B I have been considered a electron. Okay, so now here whatever the phase difference we have been found in between the two rays, the same phase difference or the similar concept we are going to be apply to find out the phase difference between these two rays. Okay, so what will be the phase difference between the two rays? Scattered from the electron which is at the center from. According to Lauge assumption, the phase difference will be, the phase difference, nothing, phase difference will be phi dash equal to 2 pi by lambda into r vector dot n vector. This is equation number 1, because this much phase difference we have been found whenever we have been discussed the Lauge method, the Lauge treatment between these two rays. Whenever we have been discussed Lauge equation, the phase difference between the two rays we have been found how much. Now I can suggest that you have to go to the note where you have been written the Laus statement. You can found the path difference is r dot n, then the phase difference between the two scattered beams is 2 pi by lambda r dot n. Here r is the position vector or distance between the two atoms. Here we can consider this is the r in case of Laus treatment, and n is nothing but is your scattering normal. The same concept also here we can apply, that the phase difference between these two rays, one is from charge, another is from the electron, will be how much? 2 pi by lambda r. Here r is the distance between the two charges, electron, one electron also charge, this is also charge, this is the distance between these two charges, dot n is the scattering normal. Okay, let this equation number is 1. So by considering Laus assumption, the phase difference we found in between these two scattered beams is phi dash equal to pi by lambda r vector dot n vector, where n vector is nothing but scattering normal, r is the position vector between the center to this charge. Okay. Sorry. So here the phase difference I have been represented by phi dash, because you can see that here the angle between this also represented by phi. So maybe confusion is going to be arise. So here phase difference I have been represented as phi dash. Now let consider a e to the power I kx minus omega t is the scattering amplitude from the point electron in the direction of n2 cap. So when the scattered beam, if we are going to consider from the electron, the scattered beam will be like this. So as it will be move along this direction, its amplitude is going to be decrease. Okay, the amplitude is going to be decrease like that. So here this is the variation of amplitude, or we can say that the scattering amplitude from the point electron in the direction n2 cap at the distance x is the distance covered by n2 cap, k is the wave number. So as it is a wave form, or it X-ray is can be represented by the waveform, and amplitude is decreasing with covering the distance along n2 cap. This is represent the scattering amplitude at distance x, suppose. Okay. Now scattering amplitude from the charge rho r dv in the same direction will be the proportional to the magnitude of the charge, and will contain the phase factor also e to the power I phi dash. See how much one electron can be scattered. The bunch of charge particles will be scattered more. So if this much amplitude is scattered by one electron, then bunch of charge particle, or suppose 3 electrons if present at here, suppose 3 electrons will be present at here, the scattered amplitude will be 3 into this much. That means proportional to the number of charge. So here hence it is written that the scattering amplitude from the charge in the same direction will be proportional to the magnitude, and the magnitude of the charge, and will contain the phase factor e to the power I phi dash. So first we have to consider the phase factor. So for the one electron which is present at center, this will be the amplitude. If we have to consider this charge, we have to consider additionally phase, that is phi dash. So hence the waveform of the amplitude which is scattered from this will be a into e to the power kx minus omega t plus I phi dash. This is the nothing but the extra factor which is represent the phase factor, phase difference factor, okay, between this and this. Okay, so this will be a e to the power I kx minus omega t plus I phi dash. But for one electron will be this much. For this much charge means inside this volume how much charge it will be? Rho r into dv. So into rho r into dv. I am going to be zoom for you somewhat. You can pause the video and you can write. Here also one thing I can suggest, that watch carefully with patience, because this video can be explained within half an hour, but in detail if it has to be explained, it will be take some time, and you have to watch with patience, then you can write the note and you can understand without any doubt. So hence I can suggest again that wherever you want, you have to watch the video repeat, and also you have to write your note properly by pause the video, because note will be help at the time of exam. Okay, now we have to move forward. Now we have to consider the ratio of the amplitude of the radiation, or the so called scattering factor will be the ratio of the amplitude of the radiation scattering by the charge element to the scattered by a point electron at the origin will be how much? This will be this much divided by this much. Okay, so df will be equal to a to the power I kx minus omega t plus I phi dash rho dr into dv by a to the power I kx minus omega t. So that will be equal to e to the power I phi dash rho r into dv. Again I am going to tell that rho r, here r is a function, okay, not multiplied with rho. Thus the ratio of the amplitude from the whole atom to that from an electron is, if I am going to consider the whole atom, then this has to be a volume integration of v rho r into e to the I phi dash dv. Let this is equation number 2. This is our nothing but the atomic scattering factor, mathematical expression of atomic scattering factor. Now V is the volume of the atom. As electrons in the atom have spherically symmetric charge distribution and rho r is the function of r only, using spherical polar coordinate we obtained dV, the small volume element in the spherical polar coordinate will be r square sin phi d phi into d theta into dr. So maybe you have been studied in your mathematics, but I am going to be explain in shortly how it will be this much. See, also you can also write in your rough for your understanding purposes. These things not to be written in for this theory of this atomic scattering factor, and no need to write in the exam also. For your understanding purposes I am going to explain how dV will be this much. See, suppose this is a spherical symmetrical things, one sphere will be there, and we are going to be consider a small element. Okay, this theta, see, this will be along, suppose this is z axis, suppose along vertical axis, this is another axis, suppose x, suppose y. So that means this theta angle is changes in this plane. Okay, and this z is perpendicular to this plane. Okay, so I am going to show you in 3D format. So suppose this is the half of the portion of the sphere, and this element is nothing but this one. Okay, at this center will be here, this center will be here, and the theta is nothing but angle covered in this way, and the phi, this this direction or this axis will be perpendicular to like this. Okay, and the phi is nothing but this angle. The phi is nothing but this angle, and the theta is nothing but this angle. Okay, so here the theta can be changed from 0 to 2 pi, and this phi can be changed from 0 to pi, 0 to pi. Okay, so this is the element whatever I have been considered over here. Now if we have to move along this direction only, so we can change the r would be changed, so here I have written these things you can write in your rough. Okay, so here this value or this direction, in this direction r will be changed, phi and theta will be constant. This portion represents, or this direction represents, r is constant, phi is changed. See, this is changes of phi, d phi. Phi will be changed and theta also constant, but this direction represents r is constant, phi is constant, but theta has to be changed. So now we are going to be consider, this is your r distance. Okay, so if I am going to put a perpendicular over here, AB, okay, then see, suppose this angle, here I taken d phi, but suppose this total full angle is phi. So this angle will be how much? This angle will be 90 minus phi. Now we have to consider the triangle AOB. Cos 90 minus phi will be how much? Will be OB by OA. OB by OA. Cos 90 minus phi, we know that sin phi will be OB by OA is how much? Is R. Hence OB distance 0 to B, O to B is the distance is R sin phi. Okay. Now BB dash, this arc will be how much? This is the radius of this arc. If I am going to consider this circle, so this arc will be, this is the distance, and this theta should have to be multiplied. So BB dash arc, okay, BB dash arc will be how much? R sin phi, this distance into this angle. So this distance OB is R sin phi into d theta. Okay. Now dV will be nothing but how much? This distance into this distance into this distance. So I am going to find out the volume. So this distance is how much? dr I have been written over here, dr I have been written over here. So this distance, this distance into this distance, if I will multiply, then I am going to get the volume element. So this much distance is dr, this much distance will be r into d phi, because this distance is from 0 to this distance, from O to this distance is r, this is d phi, so this will be r d phi. Okay, and this we found that BB dash is nothing but r sin phi. So hence r sin phi into d theta, r sin phi into d theta into r d phi into dr. Okay, so hence the volume element, how much we found? R square sin phi d phi into d theta into dr. So these things you can write in your note, in your rough for your understanding purpose. Now the volume element, hence we can use the spherical polar coordinate, we can obtain the volume element is this much, r square sin phi d theta into dr. Okay, now from equation number 1, what we can found, this is our equation number 1, this one, what we can found, phi dash will be equal to 2 pi by lambda r magnitude into n magnitude into cos theta into cos phi, because the angle between the n and r is phi. So it will be r dot n means r n cos phi. So hence it will be r n cos phi. This is the magnitude. Okay, this is the magnitude. So phi dash will be equal to 4 pi by lambda r sin theta into cos phi, because we know that n scattering normal is nothing but 2 sin theta. Whenever we have been discussed the Lauge conditions, this is, you can go your you can search your previous note where you have been written the Lauge equations derivation. You can found n modulus or n magnitude is nothing but 2 sin theta. So if I am going to put the value of n magnitude 2 sin theta, it will be phi dash will be equal to 4 pi by lambda r sin theta into cos phi. Let 4 pi by lambda sin theta will be equal to mu. Hence phi, how much we can found, that will be mu r cos phi. Let this is equation number 4. Now we have to put this value over here and dv value also over here. Now put equation number 4 and 3 values in equation number 2. We are going to get how much? Put the value 3 and 4 in equation number 2, we can found f will be equal to integration over v rho r into e to the power I mu r cos phi. Only I have just substituted, instead of phi dash I have been substituted mu r cos phi, instead of dv I have been substituted this much. Okay, so it will be r square sin phi d phi into d theta into dr. Okay, now this is the volume integration. So here d theta, I told that d theta, this is the angle of phi, this angle is theta, which is varies from 0 to 2 pi. So d theta varies from 0 to 2 pi, phi varies from 0 to pi, r can be varies from 0 to infinity, and this much I can write. So I am going to be integrate, if theta, then it will be d theta, it will be theta, and I am going to be put this limit, then I am going to get the 2 pi. So 2 pi by integrating 0 to 2 pi d theta, I got the 2 pi. So it will be 2 pi r square rho r dr 0 to infinity, and I am going to be consider the phi terms integration, then the limit will be 0 to pi e to the I mu r cos phi into sin phi d phi. Okay, f equal to 0 to infinity 2 pi r square remain over here, it will be this much, and this integral value will be nothing but this much. How it will be, I have been explained here. You have to write in your note in this side, okay, for your understanding purposes. Okay, so here the integration is 0 to pi e to the I mu r cos phi sin phi d phi is 2 into sin mu r by mu r. How it is? Let t equal to I mu r cos phi, this much. I mu r cos phi is taken as t. So dt will be I mu r minus sin phi d phi minus dt by I mu r will be equal to sin phi d phi. Then this integration will be how much? Integration over e to the power t minus dt by I mu r. So it will be 1 by I mu r integration over e to the power t into dt. Okay, here the integration limit will be how much? It will be limit c. If I am going to put cos phi will be 0, the t will be I mu r. So it will be I mu r 2. Here also I have been also considered, because this is also t na. So it will be I mu r, and the upper limit, if I am going to consider pi, then it will be minus I mu r, the I minus I mu r. So the integration of e to the t will be e to the t, the limit is I mu r to minus I mu r, and if I have to put the limiting value, it will be minus 1 by I mu r and e to the power minus I mu r minus e to the power I mu r. So if I am going to be write in the cos and cosine and sine form, this complex term, this will be cos mu r minus I sin mu r, this will be minus cos mu r minus sin mu r, cos is got cancelled, and we are going to found that 2 sin mu r by mu r. You have to write here in side by of your note for your understanding purposes. So at last we found this f will be equal to 0 to infinity 4 pi r square rho r into sin mu r by mu r into dr. Let this is equation number 5, and this is nothing but your general expression of atomic scattering factor. So if question will be asked in your exam to find out the expression of atomic scattering factor, you have to derive up to this much. Okay, so here I have additionally done for your understanding that validation of general expression of atomic scattering factor f. How much we found that atomic scattering factor? This one. This is true or false. How much it is validated, or how much this expression will be useful, that we have been discussed over here. And this, the validation of expression of atomic scattering factor f has been done by considering done by considering an experimental result of magnesium, that is atomic number is Z equal to 12. Okay, so this figure, this is the experimental result. This shows the experimental result of the magnesium. What it is along x-axis, it is sin theta by lambda, along y-axis scattering factor. So scattering factor tends to 12. I am going to do it. From figure 2, it can be found that when theta, sin theta if 0, then this value will be 0, this along x-axis value will be 0. So when theta tends to 0, f tends to z, z will be 12, z of the magnesium is 12. So when theta tends to 0, z also, f atomic factor tends to 0, tends to z, not equal to z, tends to z. Okay, one thing we have been confirmed over here. Yes, this expression also work, because here f, ideally f should have to be how much? Should have to be z. We discussed here. Okay, but experimentally it will be less than that of the z, but ideally f should have to be, ideally theoretically it will be z. So here also we found that when theta tends to 0, f scattering factor we can found equal to z or tends to z. If we have to consider the equation number 5, this one, then for theta tends to 0, also mu tends to 0, because we know that mu, because as mu equal to 4 pi by lambda into sin theta. Okay, so here theta tends to 0 means automatically mu tends to also 0. So hence from this equation we can also found that if for theta tends to 0, mu also tends to 0, as mu is equal to this much. Hence sin mu r by mu r, when mu tends to 0, I can write for mu tends to 0, sin mu r by mu r, because this is when mu tends to 0, then sin mu r by mu r will be how much? Equal to 1, because sin theta by theta, mu is very small means it will be equal to 1. Okay, because this value will be how much? Sin, we know that for sin very small theta, this will be sin theta will be theta for theta tends to 0. So here in the numerator it will be sin mu r, when mu tends to 0 it will be mu r, divided by mu r will be equal to 1, Okay, so we can get f, this f will be equal to how much? 4 pi square rho r into dr. This integrand represents the charge inside the spherical shell of the radius r and thickness dr. Hence the integral gives, this integral, if I will integrate what will it will give? It will be only give the total charge. This will represent the total charge. The total charge is nothing but the charge charge of the atom, or the so-called atomic number Z. So hence this integral gives the total electronic charge stored inside the atom, that is Z. Okay, so in this way we have been validated this expression whatever we have been derived theoretically, that is atomic scattering factor, by considering a example magnesium. Okay, so go through this video, watch this video properly. Wherever you want, you have to pause the video, you have to note, you have to write the note. I will suggest that you have to write the note, because the note only helpful at the time of exam, because in the books they have been skipped many things. So watch properly. If wherever you have to doubt, you can contact with me. Thank you so much for watching this video. Thank you.